So we're in section 4.5 today. So today we're going to talk about isosceles triangles. Anyone know what an isosceles triangle is? Anyone know what we mean when we say an isosceles triangle? What do you think, Sam?
Well, it's like two sides are the same length.
Okay, that works perfectly. So an isosceles triangle has two sides that are the same length. So we're going to say, we're just going to make it a little more strict. Isosceles triangles have, I'm going to say at least two congruent sides. So why would I say at least? Anybody know why I would say at least, not just say two? Can we have a triangle with all three sides the same? Yeah. And we still call that an isosceles triangle, because if three sides are the same, then we're guaranteed that two of them are the same. So that's why we say at least. At least two congruent sides. Now let's draw a picture of an isosceles triangle, and we're going to label its parts. So their parts get some special names. So normally a picture of an isosceles triangle, you'll see this, and we'll say that these are the congruent sides. We call the congruent sides the legs of the triangle. So that's a leg, and that's a leg. We call this angle the vertex angle. And this point up here is the vertex. We call this side, that's the side that's not the congruent side, if we only have two congruent sides, this is the base. And these angles are, down here, are base angles. So we have two legs. The two legs are congruent. We have a vertex angle up here. We have our two base angles, and we have our base. So some interesting things happen with isosceles triangles that make them kind of special. One, they're nice because they have this nice symmetry. They look nice. When you build things out of isosceles triangles, they tend to be pretty strong. So they show up in a lot of places. You can make interesting patterns out of isosceles triangles. So we're going to talk about a theorem that has to do with isosceles triangles. And I'm not big on the names of the theorems, so this is just, we call it the isosceles triangle theorem. It's really what the theorem tells us that's important. Let's just think about it for a minute before we write our theorem down to see if we can maybe have a little bit of intuition about what it's going to tell us. The isosceles triangle theorem tells us that if we have two congruent sides, we know something special about these base angles. What would you guess that would be? If these two sides are the same, what would you guess about those two angles? They're the same. It's exactly what the isosceles triangle theorem tells us. So the isosceles triangle theorem tells us that if, in words, two sides of a triangle are congruent, then the angles opposite them are congruent. So that's what our theorem says. So if we draw a picture here of a small isosceles triangle, I'm going to do it a couple of different ways here. I'm going to do this, and then this. If these two sides are congruent, then those two angles are congruent. And we can say, if we write it in symbols, if AC is congruent to BC, then angle A is congruent to angle C. And I said, that's good. So that's what the isosceles triangle theorem tells us. And it turns out that the converse of the isosceles triangle theorem is true also. So if our theorem says if two sides of a triangle are congruent and the angles opposite them are congruent, what would the converse of that be? How do we make a converse? That would be, so that was the inverse. So converse, what do we do to make the converse? Flip it around. That's right. So we would say if, how would we say it? If two, how would we change it around? If two what's of a triangle are congruent? Angles. If two angles of a triangle are congruent, then what's the other part? The two sides are congruent. That's our converse. So the converse is true also. Need an E there. If two angles of a triangle are congruent, then the sides opposite them are congruent. And we drew that in pictures. Draw it in pictures and in symbols. Or, whoops, don't want to, I could use it upside down. Like so. And this says if we know these angles are congruent, then we know those sides are congruent. And I'll label this A, BC again. And we would say if angle A is congruent to angle C, then segment AB is congruent to segment AC. So that's what the converse tells us. And the converse is true also. So that gives us a lot of information to work with if we know that two sides of a triangle are congruent or two angles of a triangle are congruent. And we know that the sides opposite are congruent or the angles opposite are congruent. So we'll talk about why this works in just a second. But I want to add one other thing, and then we'll do some examples. So any questions on isosceles triangles? Isosceles triangles, two congruent sides, at least two. We can have three, and we'll talk about what happens when we do have three congruent sides in just a minute. Legs are the congruent sides. The base angles are these angles down here. The vertex angle is the one up here. And we have isosceles triangle, the base angles are congruent. That's what we just decided. And if the base angles are congruent, then we know that the opposite sides are congruent. All right, so we're going to talk, and I think we've had a few of these before. We're going to talk about a corollary. Corollary just means, when you see that word, it just means that it's a theorem that comes really easily from something that we've already learned. We're going to talk about a corollary to the isosceles triangle theorem. So a corollary. A corollary just says that if a line bisects the vertex angle of an isosceles triangle, so before we write the rest, let's just think about what this is telling us. We have a line, so it's bisecting the vertex angle of an isosceles triangle. First off, it's an isosceles triangle. That tells us that we have at least two congruent sides. It's bisecting the vertex angle. The bisect means what? Cut it in half. So it's cutting the vertex angle in half. So we have an isosceles triangle. We're going to have a line that's cutting the vertex angle in half. Well, here's what happens. It is also the perpendicular bisector of the base. So perpendicular means what? Well, it intersects, and it intersects at a specific angle, 90-degree angle. So perpendicular means 90 degrees, and bisector means it cuts it in half. So this line that bisects the vertex angle of the isosceles triangle meets the base at a 90-degree angle and cuts the base in half. So let's draw that in the picture. So here's my isosceles triangle. Those two sides are congruent. I'm going to bisect the vertex angle. So that means when I cut this in half, that means those two angles are congruent. So I cut that vertex angle in half. What that tells us is that this bisector makes a 90-degree angle with the base and cuts that base in half. So we end up with all of these things that are congruent. We've cut this vertex angle in half. This line makes a 90-degree angle with the base, and it cuts the base in half. So I talked right at the beginning about isosceles triangles having symmetry. Well, this is the symmetry that it has. We can cut it in half, and we get two congruent right triangles. So perpendicular bisector, again, means it makes a 90-degree angle and cuts it in half. So we get the vertex angle cut in half and the base cut in half. So that's kind of a nice thing. It's very useful. So questions on the corollary. Corollary just means something that we can figure out easily from our first theorem. All right, so what I want to do next, just want to sketch out, I want to talk about how we would prove the isosceles triangle theorem. We're not going to go through the entire proof. I just want to talk about it because it's kind of related to what we did on the board for the opener, and from what we know now, it's actually pretty easy to come up with that. So I want to sketch out how we would go about a proof, then look at some examples, and then we'll talk about equilateral triangles. Equilateral meaning all the sides are the same. So sketch a proof. So what we're going to do, the idea here is we have an isosceles triangle. And I just want to talk through this a little bit. And we want to prove, our isosceles triangle theorem tells us that if these two sides are congruent, then these base angles are congruent. So that's what we want to prove. Well, here's how we're going to go about it. I'm going to sketch in this angle bisector. So I'm just going to sketch in this line that bisects that angle. Well, now we have two triangles. We have a side and we have an angle. Could we show that those two triangles are congruent? Because what do we know about this piece in the middle? And this is even before we know that. How is the length? So let me highlight this triangle in green. We've done proofs like this. We did one. We talked about this just yesterday. So I'm looking at the green triangle and the red triangle. I have a side and an angle on the green triangle. I have a side and an angle on the red triangle. What other parts do I know are congruent between those two triangles? The bisector, it shares this segment. This is congruent to itself. And what do we call it when things are congruent to themselves? The what property? Reflexive. So this bisector is congruent to itself. So these two triangles are congruent by what theorem or postulate? Side, angle, side. So they're congruent by side, angle, side. Once we know the triangles are congruent, we can say all of their corresponding parts are congruent. So the triangles are congruent by side, angle, side. So all corresponding parts are congruent. So that tells us that these two base angles are congruent. So that's how we would prove the isosceles triangle theorem. So that's not too hard. From what we already know, that comes pretty easily. All right, let's look at a few examples using isosceles triangles. So let's draw a picture here. Oops. So here's my picture for this example, and we're going to draw a few lines in here. So I'm going to call this G, H, L, K, J. I'm going to say that this, and this are all congruent. And my first question here is segment GK, it's kind of like our opener, congruent to segment HK? And if so, why? So we want to know, is this segment congruent to that segment? What do we think? Got a few yeses. So we're looking at GK, this piece. Let me put it in, highlight it in red, GK and HK. So we're looking at those two. Are those two congruent? Few more people nodding. So why would they be congruent? This triangle is an isosceles triangle. The base angles are congruent, so the sides have to be congruent. So our answer would be yes, because a triangle is isosceles. Now my next question is HL congruent to KJ? So now we're looking at just this piece and just that piece. Are those two congruent? What do we think on those two? Do we know for sure? We can't really tell, can we? We know that the big triangle, this whole side, would be congruent to that whole side because the big triangle is an isosceles triangle also, but this is only a piece of it. So we can't really tell. We're going to say can't tell. We would need more information. They're not pieces of an isosceles triangle, so we can't tell. So we're not sure. All right, let's look at another example. Questions there before we move on. Okay. Here's my picture for this one. And this question says, find x. So what are we going to do here? Can you help us out, Lydia? What would we do for this? How would we solve this problem? We just have this triangle. These two angles are congruent. It says find x. How would we set it up? What's that? We have to set them equal to each other. And why do we set them equal to each other? This triangle is an isosceles triangle. When the base angles are congruent, we know that the sides are congruent. So that means these two are equal to each other. So 7x minus 10 equals 3x plus 6. And then we're just going to solve for x. So let's go through that. Minus 3x. So I get 4x minus 10 equals 6. Add 10. 110. 10. And we figure out that x equals 4. Questions there? All right, let's look at one more example and then we'll talk about what happens when all three sides are congruent. I really like this next example. So here's our picture. And we know that this is 30 degrees. This side is 10 units long. And this angle is 60 degrees. And we'll call this A, B, C. And we want to find the length of AC. We want to find the length of this side. So how are we going to go about doing that? Doesn't seem like we have a lot of stuff to work with. What can we figure out?
the angles of A, B, C.
So we can figure out the angles of the triangle. What would we do to figure out this one here that I've marked in red? How can we figure that angle out? Subtract 60 from 180, because what do we call those two kinds of angles? They're supplementary, and we gave them a special name. They make a straight line. They're a linear pair. So 180 minus 60 is what? 120. So we can find that angle. And now we can find the blue angle, right? Because all three of the angles in the triangle have to add up to 180. So 120 plus 30 is 150. So what does that leave for this angle? 30. These two angles are the same. What does that tell us about these two sides? They have to be congruent. So this side has to equal 10. So we figured out that the triangle was an isosceles triangle by figuring out the angles, and that told us that those two sides had to be congruent. So this one we had to do a couple pieces of work before we could find our answer. We had to use a linear pair to find one angle of the triangle, add all the angles of the triangle up to 180 degrees. That told us that the triangle was isosceles, and then we could figure out the missing side. Yeah.
So that number, like opposite of 60, where 120 is just double 60, where all of them?
No, that just it happened to be that. Because 180 minus 60 is 120. So for that particular angle, that's the only time. It would be nice if it always worked that way. It'd be a lot easier to figure things out. All right, questions on that example? All right, let's talk about what happens when we have all three sides of a triangle the same. So these are more corollaries to the isosceles triangle. So the first one, our first extra corollary, extra little theorem, is if a triangle is equilateral, equilateral means what? All sides the same. Then it is equiangular. So what would equiangular mean then? All the angles the same. So in pictures, if we draw a picture here, let me grab this. So if we have all three sides the same, that tells us that all three angles are the same. And the way that we would come up with this is we would look at it as an isosceles triangle, and we would say this is the base, so those two angles have to be the same. But then we could say, okay, it's an isosceles triangle with those two sides the same, so those two angles have to be the same. So if the two angles have to be the same and they have to be that way all the way around, that means all of the three angles have to be the same. So let's think about that for a second. We have an equilateral triangle. All three sides are the same. And that makes it equiangular. So all three angles are the same. What would the angles in an equilateral triangle have to be? They have to be 60, right? Because each one's the same, they all have to add up to 180. So 180 divided by 3 equal angles, 60 degrees. So all angles in an equilateral triangle are 60 degrees. So that's kind of a nice thing. And special things happen with equilateral triangles that we'll talk about more second semester. So that's one corollary, is that if we have an equilateral triangle, that we have equiangular. The converse is also true. So how would we make the converse of what we just said here? If it is equilateral, then it is equiangular. How would we make the converse of that? If it is equiangular, then it is equilateral. So this is one corollary, and then we're going to do the converse. If a triangle is equiangular, then it is equilateral. And our picture looks just like this one, just with our arrow going the other direction. So my two triangles here. So if we know all three angles are the same, then the three sides have to be the same. So questions on what we've done today. So our big picture. If we know the two sides of a triangle are congruent, we know that the angles opposite them are congruent. Also works in the other direction. That lets us figure some things out. For an isosceles triangle, if we draw the bisector to the vertex angle, it's going to hit the base at a 90-degree angle and cut the base in half. And then these other things about equilateral triangles come from what we just talked about with isosceles triangles. All the sides are the same, all the angles have to be the same, and vice versa. Okay.